What really happens if you float away in space? The thought alone is chilling. Imagine yourself floating away into the vast, unending darkness of outer space, untethered and alone, with nothing but the stars and Earth shrinking behind you. This isn't just science fiction anymore. It's a real scenario that space agencies prepare for with rigorous training and sophisticated technology. But what if every safety measure failed, and this nightmare came true? This question has captivated the public imagination for decades. Films like Gravity dramatize it with heart-pounding intensity, but behind the scenes, the reality is even more sobering and infinitely more dangerous. Lifelines in space, the tether, that saves lives. Every time an astronaut steps out of the protective shell of a spacecraft or space station to perform a spacewalk, formerly known as an EVA or extravehicular activity, they are entering one of the most hostile environments imaginable. There is no air, no water, no sound, and no second chances. To protect against drifting into this void, astronauts are physically connected to their spacecraft with a safety tether. This isn't just any rope, it's a high-tech braided steel cable that stretches 26 meters and has a tensile strength of over 1,100 pounds. It retracts and unspools automatically as the astronaut moves, allowing freedom of motion while maintaining a constant connection to the station. But no system is perfect, especially in the unpredictable environment of space. Micrometeoroids traveling at tens of thousands of kilometers per hour, unexpected movements, or mechanical malfunctions could snap or detach even the most robust tether. That's why astronauts have a second line of defense. The jetpack that could save you, or not strapped to each astronaut's suit during an EVA, is a compact, emergency propulsion system known as SAFER, short for Simplified Aid for EVA Rescue. Powered by small bursts of compressed nitrogen, SAFER acts like a miniature jetpack. If an astronaut becomes untethered, they can manually control the system to return to safety, gliding gently back to the station. It's a simple, elegant solution for a terrifying possibility. However, SAFER has strict limitations. It contains only a small amount of nitrogen fuel, enough for basic maneuvering, but not for high-speed or long-distance chases. Worse yet, if the astronaut is unconscious, disoriented, or panicked, they might not be able to activate or control the device at all. Now imagine a scenario where both the tether fails and the SAFER unit is inoperable. The astronaut is adrift, and the only hope left lies in the hands of crewmates still inside the station. Rescue in orbit, a race against physics. In such a crisis, the astronauts aboard the International Space Station, ISS, would immediately begin contingency procedures. But here lies a sobering truth. Currently, there is no spacecraft on standby designed specifically to retrieve an astronaut floating independently in orbit. Any rescue would involve improvisation using existing vehicles or robotic arms on the station, none of which are designed for high-speed interception of a free-floating body. The margin for error is razor-thin. In orbit, objects move at speeds exceeding 27,000 km/h. Timing, trajectory, and coordination must be precise. A delay of even a few seconds could mean the difference between a successful recovery and irreversible separation. In simulations, astronauts are trained to recognize, assess, and respond to these scenarios swiftly. But if the distance grows too far too quickly, the harsh reality is that a rescue might not be possible at all. The silent drift, physics of being lost in space. Once completely untethered, your fate is dictated by Newton's laws of motion. In a vacuum, there's no air resistance, no drag, no friction, just inertia. The direction and speed of your movement at the moment of separation will continue indefinitely unless acted upon by another force. You would be completely weightless, silently tumbling through the blackness. Even the smallest movement during the moment of separation, a push of the hand, a twist of the torso, can set you spinning. There's no up or down. Your body could rotate endlessly, disorienting your senses. Could you swim back, like in water? Not at all. Flailing, kicking, or paddling has no effect. In the vacuum of space, there's nothing to push against. you would be utterly helpless. Depending on the direction of your motion, you might enter a stable orbit around Earth. In that case, you would technically be falling forever, just like the ISS itself, caught in a delicate gravitational dance. From this perspective, you're not flying away from Earth, but slowly drifting in a circle around it, just not in a way that's ever coming back to safety. The clock is ticking. Life support limits. Assuming your suit remains intact, you won't die immediately. Modern extravehicular mobility units, EMUs, the suits astronauts wear during EVAs, are marvels of engineering. They are pressurized, temperature-controlled, and self-contained. They provide oxygen, remove carbon dioxide, regulate humidity, and protect against radiation and micrometeoroid impacts. These suits contain enough breathable oxygen to last about 8.5 hours, depending on the astronaut's physical exertion and stress level. But floating alone, panicked, and using oxygen faster due to rapid breathing, that time may be reduced. It's horrifying to imagine. You're conscious, fully aware, drifting farther from your crew, helpless to stop it. Earth below, stars above, and the silence of space pressing in. You may try to call for help, but if you're out of communication range, or if no one can reach you in time, you'll spend your final hours in slow, terrifying isolation. When the suit fails, the reality of exposure. If your suit were damaged during the separation, punctured by debris or torn by equipment, the consequences would be almost instantaneous. Despite popular myths, your body wouldn't explode. But within 10 to 15 seconds, the lack of pressure would cause you to lose consciousness. Oxygen would no longer enter your bloodstream. Your saliva and tears would begin to boil due to the vacuum, not because of heat, but due to the lack of atmospheric pressure. Bodily fluids would vaporize. Your skin would swell, potentially doubling in size. Death would likely occur within 1 to 2 minutes. It would be quick but excruciating, especially compared to the slow demise from oxygen depletion in an intact suit. Could you fall back to Earth? There's another chilling possibility. What if your trajectory sends you downward toward the planet? Would you fall back to Earth and crash? Not exactly. If your path intersected the upper layers of the atmosphere, you would meet a fiery end. You'd burn up in a matter of seconds, much like a meteor. The temperatures from re-entry friction can reach over 1,600 degrees, 3,000 degrees. The suit wouldn't protect you. Nothing would. However, unless you were already on a sharply descending path, you're more likely to enter a decaying orbit that takes hours, days, or even weeks to result in atmospheric re-entry. A history of near misses. Despite the dangers, space agencies have never lost an astronaut to a float-away scenario. But there have been close calls. In 1984, NASA astronaut Bruce McCandless became the first person to fly untethered in space using an early version of SAFER called the MMU, Manned Maneuvering Unit. Though the event was controlled, the risk was real. Other astronauts have experienced tethers slipping, jets failing, or communication blackouts, but each time, training and equipment prevented catastrophe. Spacewalks are rehearsed dozens of times on Earth, in giant pools and simulators, before anyone ever suits up in orbit. Why it's still a risk today. While modern safety measures are robust, the float-away scenario remains one of the most feared possibilities in space exploration. It underscores how dependent astronauts are on systems, tools, and human coordination. A single failure, or a string of small malfunctions, can escalate quickly into a life-threatening crisis. NASA, ESA, Roscosmos, and private space firms like SpaceX all treat this as a high-priority risk. Improved tethers, automatic return systems, robotic retrieval technologies, and AI-assisted monitoring are all being researched to ensure that floating away becomes not just unlikely, but impossible. The emotional toll. Beyond the science and engineering lies the human side. Imagine what it's like for the crewmates watching their colleague drift away, helpless to intervene. Imagine being the one floating away, watching the spacecraft disappear. It's not just a technical failure, it's emotional trauma, psychological stress, and existential dread rolled into one. This fear is drilled into astronauts through their training, not to paralyze them, but to prepare them. Because fear in space isn't your enemy, unpreparedness is. In conclusion, a sobering reminder of space's power. The image of an astronaut drifting into the stars is poetic, haunting, and tragic. But it's also preventable. The best minds in aerospace engineering work relentlessly to ensure no one ever has to live that nightmare. Still, space reminds us of our fragility. It demands humility, vigilance, and respect. Because out there, in the silence beyond Earth's cradle, every choice counts, every tether matters, and every moment is borrowed time. So the next time you look up at the night sky and see the International Space Station streaking overhead, remember, each glowing dot is not just technology, but a promise that we do everything in our power to bring every explorer back home. If this expanded explanation inspired you or gave you a deeper understanding of the realities of space, please like, subscribe to Space Future Now, and share your thoughts in the comments. Let's explore the universe together, safely, boldly, and always with wonder.